So rational exponents and radicals is going to be the title of this page. Find a Sharpie. So rational exponents. And I actually probably need to move this down so that you can see it. And radicals. So the stuff that we did in chapter 3 when we talked about simplifying radicals, like the square root of 27, that's going to come up this chapter. Again, we're going to be doing simplifying radicals. There will not be any imaginary numbers this chapter. I don't think. There shouldn't be. But we will be doing roots of negatives. Just depends a bit on what kind of root. So we'll talk about that when we get there. You should be familiar with the square root of 4. Okay, that should be something that we all can do. Square root of 4. What are two numbers that multiply to make 4 that are the same? Now, the thing that we don't write when we write this is that there's a 2 here in the square root. And that 2 tells us how many numbers we're looking for that are the same. Right? So when we're doing square roots, we're looking for 2 numbers. But that doesn't mean that it's always going to be a 2. So this chapter is a lot about what if this number is not 2. But it's also about the fact that when we're talking about exponents, really, you can put any number in an exponent. Now, some of this is going to be counterintuitive, and so we're going to try and work through some of the justification for how negative exponents work and some of the justification for how fraction exponents work. But in general, this is the same as 4 to the 1/2. Okay, so what we're doing is we're taking the 2 here from our radical, and it's becoming the denominator of the exponent fraction. So these are the same thing. You have probably not seen it written this way before because you've mostly just been using radicals, but this is the same. And I should have made this 2 red because I wanted to make sure they matched. And this is just 2. Right, so the square root of 4 is the same as 4 to the 1/2 power, and that equals 2. Now, it's not just square roots. This chapter, we're going to be doing higher order radicals, which means bigger numbers where this 2 would be. So this is the cube root of 27. We're looking for 3 numbers that are the same that multiply to make 27. So we could do our factor tree, or we could just remember that it's 3. But also, okay, this is the cube root. I can write this as a fractional exponent. 27 to the 1/3. It's almost like we're saying, what's 1/3 of the multiplication that makes up 27? But not exactly, right? So we're not dividing 27 into 3 equal, we're finding 3 equal pieces that multiply to make 27, but we're not dividing 27 by 3. In this case, we are because 27 happens to be, well, no, we're not, because when you divide 27 by 3, you get 9. But the answer to this is 3. Okay, so we're splitting it up into 3 equal pieces of multiplication. That's why it's 1/3. And you could also do, your factor tree. 3 and 9, and then 3 and 3, and then we have 3 numbers that are the same. Give us a third. 3. Okay, so the way we would read this is you would say the cube root of 27. Square root and cube root are kind of be the ones with names. The other ones you would just say Oh, that's the fourth root, or the fifth root, or the sixth root, if this number was 4, 5, or 6. But the cube root is a special one, just like the square root. This would be the square root of 2, right? Oh, of 4. Goodness. Misspeaking a lot. So something special about these odd roots, right? So we have an even root here because it was a 2, and an odd root here because this is a 3, and 3 is an odd number. Odd roots have real solutions of negatives. And I know I need to move it up. Odd roots have real solutions of negatives. So before we had the square root of a negative number, it would become it's imaginary. There's not a real number in the real numbers, like positives and negatives, that can multiply by itself to make a negative, because if you multiply negative times a negative, you get a positive. So you need an imaginary number. But odd roots are different because there's 3 numbers, or 5, or 7. There's an odd number of numbers being multiplied by themselves. And so you can have negatives inside and get real roots. Like, for example, the cube root of negative 343. Now, a lot of these, off the top of my head, I would not just know them. So it's okay to have a calculator next to you or type these into Desmos. But I expect exact answers. So if you're getting like 7.178, like a bunch of decimals, you need to simplify that radical and write it in radical form. Hopefully that makes sense. Basically, we should only be using the calculators to check our answer, not just put in decimals as our answers. This, though, is divisible by 7. So this is the same as the cube root of negative 7 times negative 7 times negative 7. 3 negative 7s, right? Because a negative times a negative makes positive, times another negative makes a negative number. So this is just negative 7. So because there are an odd number of numbers, because we're looking for an odd number with the roots, we can have an odd number as our, a negative number as our solution. Okay. There's some ones that should become fairly consistent. You should know that the cube root of 8 is 2, right? 2 times 2 times 2 makes 8. Cube root of 8 is 2. But a lot of these I don't expect you to memorize. You could use our factor tree guess and check method where you just divide it with a calculator until you find a factor and then do the factor tree. That's fine. We'll do that in a bit too. Okay. The other kind of important thing to note is when we're doing even numbers or even roots, this is the fourth root of 81. So 81 is going to be 9 and a 9, and then these are both 3s, right? So I have 1, 2, 3, 4 3s. So this is 3, but because it's even, it's also negative 3. Right? So last chapter we were doing plus or minus because you take the square root of both sides, you get a positive or a negative number. This could be either or both. Not sure which, actually. Because if we do a negative times a negative, do a negative times a negative number, and a negative times a negative number, this is going to be a positive number times a positive number. So this is just a positive number. Yes, Alejandro, I'm recording them. Yeah. So we just get a positive number with 4 negatives. If I have 3 negatives, though, we get a negative number. Okay, the other thing that's going to come up, I'm not sure about right away. I don't remember if this sort of thing is in the homework, but I just want to show it to you, is that we're going to have complex radicals. Or in other words, it's not going to simplify perfectly. So the cube root of 8 was 2. The cube root of 16 is not going to just be an integer number, right? This is going to break down to be 4 and 4, and then that gives 2, 2, 2, 2. I have 4 2's being multiplied to make 16, but I'm only looking for 3 numbers that are the same. So we'll do it like this. So those 3 2's come outside, and so it's 2 times the cube root of the one that's left, and that goes inside. So this is just like the simplification we were doing last unit when we were simplifying radicals, like the square root of 27, right? It's 9 and 3, and so it's 3 root 3. The cube root of 27 is just 3, but the square root is a complex radical. We have to write it as multiplication. So you're going to have this again this chapter. Excuse me. So that's kind of overview of higher order radicals. And we can rewrite all of these as fractions, right? This is 81 raised to the quarter. This is 8 raised to the third. This would be raised to the third as well. Okay. Now, I want to take a pause on this, and we'll come back to it. Please let me know if I'm going too fast, because I don't want to just zoom through. And we're going to talk about the exponent properties, because we are going to do fractional exponents, and not just like to the 1/3, right? Not just this, but complex fractions where it's like 3/2 or 2/3 or something like that. So our first piece is going to be all the exponent rules. Excuse me. All the properties of exponents. So I'm going to use a different piece of paper for this, and we'll come back to those notes to finish them. And if you ever need me to move the paper, go slower, go back to something, let me know. Okay, so properties of exponents. You've seen all these before. All of these before. Pretty sure all these before. If not, well, we'll see them now. There's going to be, I'm going to do 2 columns. So this side of the paper is going to be 1, 2, 3, 4, 5 properties, and then 1 on this side, but this side I'm going to use about the same amount of space because I have a longer explanation for it. So for each of these, it's going to be, they'll look like this. Don't worry about that negative exponent. I need another piece of paper. We're going to come back to this. So the product property. Each of these I'm going to do kind of the definition, what it looks like with only variables, and then I'm going to show you something that it would look like when we actually use it. And then in red will be kind of an explanation of how it works. So the product property just says if we're multiplying things with the same base, a being the base, we add the exponents. Just combine the exponents. So like if you have x squared times x cubed, well, that's x to the 2 plus 3 power, which is 5. And that works because an exponent is just repeated multiplication. We're just counting how many times did we multiply x by itself. So here we did x times x, and here we had 3x's being multiplied. So how many in total did we have? Well, 5, right? So I have the 1, 2 here for the x squared, and I have the 1, 2, 3 here for the x cubed. So this means I really have 1, 2, 3, 4, 5. I have x to the 5th. So the shortcut, instead of writing this out every time, don't do this. The shortcut is just add the two exponents together. This is the basis for all the other properties. So that's the product property. We can combine our exponents as long as we have the same base. If the base was different, we cannot combine them. They're not like terms. Okay. So that's the product property. Then we have a power of a power. The justification for this is this product property. So the power of a power is just we have some number raised to another number. And all of that has its own exponent. And so what we would say is, okay, we would multiply m and n. So we can combine this by multiplying those two exponents. For all of these, sorry, goodness. For all of these, it's expected that you be able to go both directions. So generally, we're going to go from left to right. We're going to turn x squared to the third power into x to the 2 times the 3, which is x to the 6th. So generally, we're going to go in this direction. But sometimes we would need to go the opposite direction. We would want to make this more complicated for some reason. Now, not really with this power of a power, but definitely sometimes with this product property. When we talk about exponential functions, we will be using this. So the justification for the power of a power here is that, well, if I have x squared to the third, this to the third just means I'm multiplying 3 of these together. X squared, x squared, x squared, I have 3. But if I'm multiplying 3 of these together, they all have the same base, then I can just add their exponents. That's what this said. So we do 2, 4, and 6, right? I just add all the 2's together and I get x to the 6th. There's 6 x's here being multiplied. So power of a power is just the product property to make this easier. Okay, so we would multiply the 2 times the 3. It doesn't matter what the numbers are. If this was a 5 and a 10, you'd multiply them, you get 50. Now, I was saying we should be able to go both ways. That's not really going to happen very often with the power of power, but with the product property it is. Where did that piece of paper go over here? So you don't need to write this down, but in later chapters, later sections, if we have an exponential function, we have 2, and then there's an x in the exponent, and we would add something to that x. This can be arranged, right? This is just m plus n. A is 2, x is m, 3 is n. I can rewrite this as this multiplication, right? I'm going from this side and I'm rewriting it this way. And then I can rearrange it by putting the 2 to the third in the front, and that's just 8. And so 8 times 2 to the x is the same as 2 to the x plus 3. These are equivalent functions. They really don't look like it. This does not look the same as this, but they are the same because 2 to the third is the 8. Okay. We'll also be using this when we do logarithms. But this is going to be in the spring, probably like February or March. Okay. So you don't need to write that down. I just wanted to. So we want to be able to go both ways with these product properties. They work in both directions. Okay, so I have the power of power, I have the product property, and then we have the power of a product, which just means the names for these are what they are. We have a product inside here. We're multiplying a times b raised to a power. We can actually split this up into 2 pieces. This example is true, but I'll provide another one that's, I think, probably better. So if I have 6, I can split that up into being 2 times 3, and then I can raise both of those pieces to a power, and I'd get 4 times 9 is 36, which is this. It's the same thing. The other thing that we should be able to do is, like, if we have, you don't need to write this down unless you want another example, 2x to the third, well, I should be able to say, well, that's 2 to the third times x to the third. And so this is 8x to the third. So hopefully that makes sense. I have two things being multiplied inside the parentheses, all raised to a power. I can split those things up, say 2 to the third, x to the third, and then simplify that. That might be useful. This, with the number, probably not so much. But this, maybe. And we should be able to go both ways. We can turn that 8 back into 2 to the third, and we can put it in the parentheses. We can combine it all. Why you would want to do this depends on the problem. Don't know why. So you don't need to write that down. Just another example. Maybe a better example than the number one. Okay. Now, we're going to talk about this next one, and then we're going to use this column on the right to talk about fractional exponents. Or not fractional. We're going to talk about negative exponents first. So first thing, these next rules are going to all have to do with specific kinds of exponents. So this one is the 0 exponent. If we raise anything to the 0 power, it is 1, except 0 to the 0. We're not going to do that. That would be a calculus problem that we're not going to worry about. So 0 to the 0, we're not going to worry about that. But any other number, if it's 0 in the exponent, it just turns into 1. So it doesn't matter what that number is. There has been in history some argument that this is not how it works. I think intuitively our brain wants to say, oh, it should be 0. We're going to talk about why that doesn't make sense in a minute. It has to be 1. Something raised to the 0 power has to be 1 for our math system to make consistent sense. And so we're going to do an example to show that in a minute. But first, we also need to talk about negative exponents. So if we have 0 in the exponent, it's 1. And then what do we do with negatives? So I'm going to tell you what it is, and then we're going to justify it. A negative exponent turns into a fraction. So if I had, say, 2 to the negative third, actually, let me just do all this red part here. So negative exponent, 2 to the negative 3, becomes 1 over 2 to the third. So we take whatever is inside the base of the exponent, we flip it over, and then we can simplify it. That also means if we have a fraction in our exponent and it's negative, we just flip that fraction over. It's also going to mean some other things about moving denominators to numerators, but we'll get to that later. But in general, if we have a negative exponent, it becomes a fraction, or it flips over. Really, this is 2 over 1, and so we're flipping it over and it's becoming 1 over 2 cubed. So this fraction here, this 2/3, becomes a positive exponent, and we flip the fraction over, so it becomes 3 over 2, and then we can simplify that 3 over 2 and square it, become 9 over 4. This is really important. These fractional exponents, these negative exponents become fractions. They don't become negative, right? This negative exponent does not change the sign. Now, why would it work this way? Why would this possibly be the way that it works? To justify this, we're going to do an example where we list out the exponents. we simplify them, and then we work our way backwards. Okay. And if I'm going too fast, you need me to go back up, please let me know. All right, so we're going to do a bunch of 2's. And we're going to start at the bottom. So 2 to the negative 4, 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0, which we already talked about. Now we're going to show why. We're going to do these first 4 first. So 2 to the first, 2 squared, 2 to the third, 2 to the fourth. I would like you to simplify those on your own to the right here. All right, so list all these out. We're going to put numbers next to them. But start with 2 to the fourth, and then do 2 to the third, and then do 2 squared, and then do 2. And there should be a pattern that we recognize. So just a little bit of time to get caught up there. Okay. So let's start with 2 to the fourth through 2 to the first. Oh, whoops. There we go. So 2 to the fourth is 16, right? That's 4 times 4. 2 to the third is 8. 2 squared is 4. 2 to the first is 2. What are we doing every time? Well, if we're going this direction, if we're going down, if we start here at 2 to the first, we're multiplying by 2 every time. It's doubling. So the next one would be 32, and then 64, and then 128, right? We're going to multiply by 2 every time. But if we think about this going the other way, going up the line, we're dividing by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 has to be 1. It does not make sense for 2 to the 0 to be 0. It has to be 1. So that's the justification for 2 to the 0 being 1, because it makes sense in our pattern of what it means to be an exponent. What it means to be an exponent is we're multiplying over and over and over. But it also means we're dividing over and over and over, depending on which direction we're going through our list of numbers. If I'm going up, then I'm multiplying. But if I'm thinking about it going down, then we're dividing by 2. If I start at 2 to the fourth and go down every time, we're dividing by 2, which means to go to the negative 1, I'm going to divide by 2 to get a half. Right? 1 divided by 2 is 0.5, or 1/2. So we're keeping things as fractions. And then this is a quarter. If we divide a half by 2, half of a half is a quarter. Half of a quarter is an eighth. Half of an eighth is a 16th. You'll notice there's a pattern here. Not just are we dividing by 2 every time, but the numbers on both sides match, right? So I have 16 and I have 16 here. I have an 8 and I have an 8. I have a 4 and a 4. I have a 2 and a 2. So negative exponents have to be fractions. Negative exponents are fractions. Sometimes it's going to be 1 over something. Like in this case, it's 1 over 2. Sometimes it won't be. What if what's negative 2? Oh, the base number? I mean, like instead of 2, it would be negative 2? Well, then your sign is going to switch. Right? If this was negative 2, then it would still be 1, but then it would be negative 2, positive 4, negative 8, positive 16. You're switching sign because you're multiplying by negative 2 every time. Your sign is going to switch every time. So the values wouldn't change, but you'd have negatives kind of every other number through the list. I assume you mean the base, because if it's negative 2 in the exponent, then you just get a quarter. Yeah. So we're not going to really do negatives in the base because they do that sign switching. Well, we will. We're not going to graph them. Sorry. We will do that. We will simplify those, but we won't do what? We won't do the graphs. We're going to get to exponential functions where the x is in the exponent, and so we're multiplying over and over. I think you did these in Algebra 1. Maybe not. Depends on last year. No, you guys would have had geometry last year. I don't know what I'm talking about. So, negative exponents make fractions. Okay? And then we have the quotient property, which is related to this. Okay, so we have one more property. So we did zero exponent, we did negative exponents over there. Last property is the quotient property, and this can be thought of as in two ways. One, and I'm actually going to add something here. For one, we have the same base, and then we have an exponent on the top and an exponent on the bottom. These can be combined as a to the m minus n, so we would subtract. So before we said multiplying, we add the exponents. Here we're saying when we divide, we subtract the exponents. We should be able to go both ways. If we have the subtraction, we should be able to turn it into this division. And our example would be like x to the fifth, x squared. These have the same base. And really, we're just saying, okay, if I divide 5 of these x's by 2, I can cancel these out. And I'm left with x cubed, which is 5 minus 2. The other way to think about this is really we're doing a to the m over 1 times 1 over a to the n. And so this can be rewritten as a negative exponent. You don't need to write this. I mean, you can if you want. So I can rewrite this fraction as a negative exponent because it was a fraction. So I do the negative exponent. And then our product rule just said, oh, we can add these together. M plus negative n. And so we would get a to the m minus n. Most of these we're not going to worry about this chapter. They're going to come up when we do logarithms again. And so we're going to use kind of different ones of these more often, depending on which unit we're in. This unit, we're mostly just going to use the power of a power, actually. Power of a power. So those are our exponent properties. And the reason we talked about those was so that we could use the power of a power to simplify fractional exponents. It was all that for one of them, but I wanted to go over all of them because they're all important. So I'm going to go back to my other paper in just a second. If I can find it. Where did I put it? Over here. Okay. So back to the other paper. Hopefully we had enough time. So fraction exponents, we're not just talking about like x to the 1/2, because that's just the square root. Exponents. These are going to have a numerator that's bigger than 1. I mean, really, this works for any fractional exponent, but we're concerned about the numerator and the denominator not simplifying. So we have things like 3/5, 2/3, 3/2, 3/8. Those kind of fractions where, oh, it doesn't reduce, it doesn't simplify at all. It's just, that's the fraction. And so here's my example. So 16 to the 3/2. So we need to remember something about fractions. We can rewrite them as multiplication. So here we have a numerator, that's the top, and the denominator. And for this problem, it's 3 over 2, right? 3/2. This can be rewritten we can rewrite 3 halves as 3 over 1 times 1 over 2, which is the thing that's going to help us actually simplify this fractional exponent. So this 16 is really 3 over 1 times 1 over 2. Now our product rule said if we had exponents being multiplied, that's really the same as 16 to the half to the third, right? I can rewrite this as a power of a power, or the square root of 16 to the third. Either way. So because we have this 1/2, that's the same as the square root. Either way. And at this point, now we just simplified the square root and cube it. So this is square root of 16 is 4 cubed. These are both going to be the same. 4 cubed is 16 times 4. This is 64. Now, sometimes, really, there's a shortcut here, and that shortcut is to just take the 16 to the 3 halves and rewrite this as the denominator goes into the root, and the numerator goes as the exponent. So you can do this if you want. You can also turn it into a fraction. But either way, there's a shortcut here. We're not going to really go over that shortcut more than what I just said, but there's a shortcut. This process is not the most intuitive thing. Okay, so recognizing, well, the process is not that complicated, right? We're just splitting up the fraction, making something a root, and raising it to an exponent. That process is fine. But the intuitiveness of exponential fractions is really hard on our brain. These are not things that I look at 16 to the 3 halves, and I'm not going to simplify that in my head immediately. I might do all the steps in my head. I can do 16 to the half and then raise it to the third in my head. I can keep all these numbers straight in my brain to get to 64. But I don't immediately go, oh, 16 to the 3 halves, that has to be 64. That is not a thing that I expect of anybody. If you can do that, then we should probably have a conversation about your future schooling, what college classes you should take, kind of thing. Because like 16 to the 3/8, that's a thing that exists. I don't know what that simplifies to be. I could figure it out, right? But I don't just intuitively know how those fractions look. And so we're going to do an example in a minute to try and help us understand the pattern of how they work. But really, it is truly not the most intuitive thing. Okay. Let's do one more example, and then I want to do the pattern. Oh, where did I put that example? Here we go. 32 to the 3/5. So this would be, if you can use the shortcut, you would do 5 root 32, fifth root of 32 cubed. So the denominator goes in the radical, the top stays as the exponent, and then we would simplify this. This is also the same as 32 to the 5th cubed. These are the same. I don't care which process you use or how you want to think about it. But in any case, the 5th root of 32 is 2. Cubed is going to be 8. This should not be the most surprising number. We are we'll talk about the pattern in a second, but How do I want to explain this? 3/5 is smaller than 1. So our answer is going to be smaller than 32, right? 32 to the first power is 32, and 32 to the 0 is 1. So our answer, because this fraction is between 0 and 1, is going to be between 1 and whatever the base is, which was 32. So 8 should make some sense. It's 3/5 of the multiplication of 32. In other words, 1/5 of the multiplication is 2, and 3 of those 2's makes an 8. So this is the 3/5. Explaining fractional exponents is, oh man, not my most favorite thing. I like fractional exponents. Explaining it, it's counterintuitive. So you should get 8. You don't need to write this list down. This is like the other list that we did, where we did all the negative exponents. And you could do negative exponents here. You would just get fractions of all these things. And I picked 4 for a reason, because square root of 4 actually works. And so if we're doing increasing fractions with a square root, it's a lot easier to see the pattern here. Now, what's happening? If we ignore this number, if we ignore all the fraction numbers, that number, that number. So here we just have 4 to the 0 is 1, 4 to the first is 4, 4 squared is 16, 4 to the third is 64. Okay, so those are the integer exponents. Now, 4 to the half is 2, right? The square root of 4 is 2. And now I hope the pattern emerges here with the fractional exponents, because we're going to add a half to everything, so to every exponent. So this is 4 to the first. It's going to become 4 to the 3 halves. 3 of these halves multiplied is 2 times 2 times 2. Or really, we're just going to multiply this 4 times 2, and that gives us 8. If we multiply by another 2, if we add another half, if we add another square root of 4, we get to 16. If we add another square root of 4, 2, by adding, I'm saying if we multiply by another square root of 4, we get 32. And then we get 64. So the fractional exponents are breaking the multiplication down further, and then sometimes building it up, right? Because 5 halves is going to be 5 of these 2's multiplied together, which gives us 32. There's a number of ways to think about it. Okay. Your homework is already in Teams, and it's doing this. It's simplifying these fractional exponents and simplifying higher order radicals. It's only 4 problems, I think, or 5. I don't remember exactly. But it's not very many, because we're going to have another homework assignment this week. So there you go.